All right, you ready? Where's the attendance sheet? Okay, so if you haven't signed that, you got here a little later than when I passed it out. Make sure that you get it before the end of class or before you leave today. And then today's a Tuesday, so make sure that you turn in your homework. Oh no, I'm sorry. That's next or this Thursday. So I gave it to you later. Okay, so Thursday, hand that in to me. Just a reminder then. Any questions before we get started? No? Hopefully things haven't been too difficult. Homework's okay. Good. Oh, okay. All right. Well, if anything does start getting difficult, or you find an issue with something, let me know as soon as possible. That way I can fix it quickly for you. Okay. So last time we did Bernoulli equations, correct? Yeah. Okay, so we remember that. Today we're going to do one final substitution class of differential equations, and then later on with second orders we'll do some similar stuff. But for now, this marks the end of our foray into substitutions. So today we'll talk about equations with constant coefficients, and constant coefficients is a bit of a lie. There's another thing that we'll call constant coefficient equations, so keep that in mind, that the same words are used for different things in this class. So we'll start out with what I mean by this. Then we'll work through an example solving it. I'll have you do one example by yourself, and then we'll work through the general solution. And I figured if we have time, I'll go through exact and inexact equations, because those, I think one of the problem of those does show up on your project one. I may not necessarily ask that sort of problem on your tests, but good to know what they are at least. All right, so what is an equation with constant coefficients? Well, it's one that can be written this way. And this looks a little weird. I think we might have seen this sort of form before, where we sort of separate the dy dx as a fraction. And we have these two coefficients here. So the constant coefficients part in this type of differential equation is referring to these real numbers. So normally we think of, or we write out differential equations that are linear in terms of functions of x. Here, these are functions of both x and y, but they are linear in x and y, and these a, b, c, and d, e, f are constant. So that's what constant means in this case. We can rearrange these to look like this. The reason that it's formatted this way is because sometimes you will get differential equations in this form. This sort of thing pops up in a multivariable context a lot. And then you can rewrite these as an ordinary differential equation here. So you're not doing any multivariable stuff, and solve for y as a function of x. Okay. And this should look sort of familiar. We've seen things like this before when we started doing substitutions. And here's why. When you set c equal to f equal to 0, we get an equation that looks like this. Can you classify that type of equation? So I'll give you a minute or two. Figure out what kind of equation that is that we have already solved. Claim that you do know how to solve this. Check some stuff, go ahead.
No,
Okay, has anybody figured out what kind of equation this is? Don't believe it's separable. Yeah, I don't think it's going to be separable. It is homogeneous. Yeah. So this is a homogeneous equation in X and Y. So yeah, so there's a lot of stuff that we have to check to classify these equations at this point. We've seen probably 4, 5, maybe 6 different kinds at this point. So there are a lot of different techniques that you want to remember. And it's really, really helpful to know how to classify them ahead of time. So that you say, all right, this technique goes with this kind, as long as I can classify it as a homogeneous equation or a Bernoulli equation, I know how to solve it right away. I can just immediately write the solution. Okay, yeah, so this is homogeneous in X and Y. So we have this rational function right here, and you can factor out X from top and bottom, and then get this, and note this is a function of Y over X. That was our original definition of homogeneous. And then we also had the definition that said, all right, take this, write it at, think of it as f of xy, and then check f of tx, ty, is this equal to f of xy? Okay. That was your second way of checking for homogeneous equations. All right. And then here I have a little footnote that tells you one sort of third way to check. You just note this is a rational function, and that all of the terms that are added together in the top and bottom have the exact same degree. These are linear, 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 linear. So everything cancels out when you put in tx. All right, what next? So now we're going to talk about solution methods. So we have an example here to work with. Dy dx equals this big rational function. And we want to figure out how to solve this thing. As usual, we have a class of differential equations. Can we find a general solution for it? So here's our idea. We like homogeneous equations. I know how to solve those. They're a little tedious to work through the substitutions, but we've done them before. We can do it as long as we can turn this into one. So maybe we can do some sort of substitution that turns this differential equation into a new differential equation that is homogeneous. And the idea is, well, if I substitute something for like y here, maybe I can get the 13 and the -5 to cancel out. So let's see what happens. While we're working through this, we've got the numerator and denominator are linear in both x and y. So let's rewrite that differential equation up here. dy dx equals 7x minus 9y, I think, plus 13, and x minus y minus 5. Make sure I got the 9 right. Plus 9. Okay. So it should be, like I said, really easy to just make some sort of substitution here for y that, maybe cancels out the 9 and then leaves us with, v minus 13 or something here. So we try a substitution that looks like this, where y is equal to v plus k. It's a linear transformation, translation of some variable v. And then we say, all right, k is a real number. It's fixed, but I don't know what it is yet. And then we'll perform the substitution with that parameter k in there. I won't know what it is yet. And then we'll figure it out later in order to cancel out those constants, the 13 and minus 5. And then there's another footnote here. This is a general technique, very general technique. It's called an ansatz. And it just means kind of making an educated guess at a solution based on some, hunch or some sort of prior information that you already have seen before when you're solving these types of things. So I have a good idea, and I make a guess to see if it works out. All right. So we want to solve for y and dv dx. Did I give myself space for that? No. Okay. So we have already y equals v plus k. And we want dv dx. Okay, well, dv dx by the chain rule is, or actually we can just differentiate this directly. We'll need the chain rule later on, is immediately dy dx. If I differentiate both sides of this, then I cancel out, or the k disappears because it's a fixed real number, and then I just get dy dx on that side. Okay. Nope. So let's see what happens here as we go through this. Dy dx, we know, is this rational function in y and x minus y minus 5. And so we want to plug in v plus k for y, and we'll get 7x plus 9 times v plus k plus 13 over x minus v plus k minus 5. Okay, and we want to cancel out 13 and minus 5. Let's maybe try to cancel out the 13 first, just because it's on top. So we can multiply everything out and collect everything that doesn't have x or v in it. 7x plus 9v plus 9k plus 13. And then in the bottom, we've got x minus v minus k plus 5. All right. So if this is going to be equal to 0, we can now solve that for k. So we've got 9k equals minus 13, and so k. All right. Question? No, because there's a minus out here that distributes to minus k, and then you get minus v minus k minus 5, and then I factor out a minus from there. I did skip that step though. Okay, so we've got a value for k. Does it work? Well, it certainly works for the top constant, makes that 13 go away. What about the bottom? I'm now out of parameters. I only had one parameter k, and I need to make sure that this also is equal to 0. So does this work? Well, if k is minus 13 over 9, then k plus 5 is minus 13 over 9 plus, and then 5 is 45 over 9, which is definitely not equal to 0. Uh-oh. I've run into a problem. Okay, well, what if I solve for the bottom equation first? Then I get k plus 5 equals 0, k equals minus 5, and hopefully you can see where this is going. Now I've got that this one will work. I'll get a 0 out for k plus 5, but I won't get a 0 for this because now I have 9 times 5 is 45 plus, 9 times minus 5 is negative 45, plus 13 is not 0, and I'll be left with a constant on either the top or bottom, no matter how I do this substitution. Okay, so my first idea did not work. It's still a good idea, though. It looks like it should work, just have to modify things a little bit. So we have a second idea. So we were able to get one constant to disappear because we had one parameter and we could choose it so that it disappeared, or so that maybe C or F disappeared. If we have two parameters that are independent of each other, maybe we can do something like choose one to cancel the C and then choose the K to cancel the F. So let's try something like that, where we make a substitution for both variables. And here we are maybe thinking a little bit of some multivariable stuff, where we have that f of x, y, let's see there, is ax plus by plus c over dx plus ey plus f. So if that thing is thought of as a multivariable function, we can do a change of variables. If you've seen the Jacobian before, then you know what that is. Okay. So we want to transform the right-hand side of our differential equation. Let's write that down real quick. We've got dy dx equals 7x plus 9y plus 13 over x minus y minus 5. And if we use these two substitutions, we should get, well, 7, and I just replace x and y, u plus h plus 9 times v plus k plus 13 divided by u plus h minus v plus k minus 5. Okay. Same thing I did before. Multiply everything out, collect all of the constants. So we have 7 times u. Maybe I should note u, v are the variables here, so everything else goes into its own term. 7u plus 9v plus 7h plus 9k plus 13 over u minus v plus h minus k minus 5. Now I want each of these equal to 0 for the same choice of h and k.
Is the idea that by introducing another constant, you guarantee that the system has a solution?
Exactly. Yes. So when we make that first substitution that didn't work, we have that one parameter, and okay, we can solve one of those equations. We can't then introduce a new function for x, at least a linear one, that will cancel the other constant. Because when we do that, we end up with the same problem of having a constant either on the top or bottom while we cancel out the other one. Right? So you have to do them simultaneously. That is important. Okay, so given this, let's see if I gave myself space. I did not. I thought I gave myself space on this one. That's fine. We want to solve this for h and k. So we have 7h plus 9k equals minus 13, and h minus k equals 5. And those of you who remember your algebra, or maybe your linear algebra, know that you can write this as a matrix equation. 1 minus 1 hk equals minus 13, 5. And then I'll just go ahead and invert that and get us our solutions. We have hk equals, is that 1 over minus 16, I think? Yeah. And then minus 1, minus 9, minus 1, and 7 times this thing. Okay, so don't worry too much about how I got that. The point is that we can go ahead and solve that by any method you like, and we get out some solutions. So here we get h equals 13 minus 45 over negative 16, which is, I don't know, 32. I think it's 2. And then k equals 13 plus 35 over minus 16. And this should give us 48 divided by 16, minus 3. Okay, so there are our values of h and k. And if we bring those back up here, we can write down our actual substitution. X equals u plus 2, and y equals v minus 3. We okay at this point? We're going to start doing our substitution after this. Anything that you are confused about? This one?
Yeah.
I just did this because it was quicker and I didn't have the solution to this memorized. If you want to get these two numbers, you can go ahead and do like the elimination method or the substitution method here. So I guess here you would say, yeah, do that, or you can multiply this one by 9 and then add the equations together, solve for h, and so on.
Thank you.
Mm-hmm.
Will it always be x equals h and y plus 1?
Yes, this is a very specific type of substitution. The same way that homogeneous equations required the substitution, what was that? So we said v equal y over x for homogeneous, and that was the only substitution that worked for that. This is the only one that works for these types of equations. Mm-hmm. Yep, good questions. Okay, so let's go ahead and use these now. So we figured out what x and u, or what x and y need to be substituted with. What about dy dx? Well, it's a little trickier, but we use the chain rule. The actual substitution is not very hard. but it's a little weird to think about. So we have dv dx, and we want to get, so we want to replace dy dx with something that only has u and v in it, because once we substitute, we get an equation that looks like dy dx equals 7u plus 9v over u minus v. Notice the constants went away because we chose h and k so that they would. All right, and now we just need to get v and u somewhere over there. All right, so I have dv dx, and I can think, well, v is some function of x, but I can split it up into, I can factor this f as g after h and use the chain rule. So here we'll get dv du dx. And I claim this is enough because we have that x equals, or u, what was that one, plus 3, I think, plus 2? Yeah, u plus 2, which means that du dx is 1. You differentiate both sides, this term goes away, that also goes away, and leaves you with a 1. All right, so just like before, we get dv du equals this thing, except we have dy dx, don't we? Well, we're almost there. Dy dx, remember that that is v minus 3. And if you differentiate that, you get dv dx. Okay. So because we're doing this linear substitution where the constants there get differentiated away, I have all of the nice derivatives that I want. It's not very hard to get dv du. Okay. It's just, it takes that weird chain rule thinking. Okay. So our final differential equation here in terms of u and v is 7u plus 9v over u minus v equals dv du. Okay. And note, yep, that's homogeneous in u and v, whereas the first equation in x and y was not. All right. So now we just have to solve this guy with another substitution and then plug everything back in at the end. This might take a little while, but you can do it. So let's finish that off real quick. We've got dv du equals 7u plus 9v. I've written this a bunch at this point. And this is homogeneous, so we make a substitution. We use w since we can't use v again. And that should be v over u. All right. Okay. And well, that gives us v equal w or uw, and dv du equals, remind me what this one should be. If v was a y and u was an x, what would you write? Okay. If I want to take a derivative with respect to u of this thing, what rule do I use for this expression? Product rule, yes. Because w is written as some function of u, right? So product rule right here. And that gives us derivative of u with respect to u is 1, plus u times derivative of w with respect to u. That's what we end up with on the left-hand side here. And then it should be pretty easy to factor out the u here. So we can write w plus u dw du equals 7 plus 9w over 1 minus w. Right. And that comes from multiplying by 1 over u on top and bottom. All right. And then what did this substitution turn a homogeneous equation into? Do you remember that one? It's one of our favorites, one of the easier ones. Separable, yes. So we end up with a separable equation. This is separable. We just have to rearrange things with the w on one side and the u on the other. So if we do that, we get, let's see, u dw du equals 7 plus 9w over 1 minus w minus w. And if we add these together, yeah, we're gonna have to do that. Find a common denominator, add them together, and we get u dw du equals 7 plus 9w minus w plus w squared over 1 minus w. And then you rearrange things, write it separately, and we get 7, or right, w squared plus 8w plus 7. And then on the other side, we get du over u. Okay. Excuse me. This now looks like a partial fractions, maybe? Yeah, that's probably gonna be partial fractions. Luckily, this is not too hard to factor down here. So we have w plus something times w plus something, and we need factors of 7 that add to 8. I'm gonna guess 7 and 1 probably work there because we want positive 8. All right. So we can rewrite things. Let's go ahead and do that partial fraction part first, just to get it out of the way. 1 minus w over w plus 7, w plus 1 equals a over w plus 7 plus b over w plus 1. All right. And then we can do the cover-up method, make our lives a little easier here because both of the factors are linear, right? We don't have any irreducible quadratics. So let's see. This should be w equal minus 7. Cover that up, and we get a equals 1 plus 7 over minus 7 plus 1 is minus 4 over 3. that right? Yeah. And then W equal -1, if we erase that, is going to give us B equals 1 + 1 over -1 + 7, and this should be 1/3 positive. All right. And I think I gave myself a ton of space. No, I did not. Dang, where did that go? All right, so let's rewrite our differential equation here. We get -4/3 times 1/w + 7 plus 1/3 times 1/w + 1, and that's times dw. And we're going to integrate both sides. All right, those are pretty easy ones to do. Do a quick substitution if you want to, but we get -4/3 natural log absolute value w + 7 plus 1/3 natural log absolute value w + 1 equals log absolute value of u plus c. Okay. And if you want, you can go ahead and simplify things a little bit. We should get, let's see, log w + 1 over w + 7 to the 4th power, absolute value, equals 3 log absolute value u plus c. If you want, you can try and solve that for w. I don't think that's a great idea. That's going to be really hard. Why? Because you have a 4th degree polynomial there, and those are not easy to solve. So for these ones, I would suggest leaving it in some form like this, and then just substituting back in. I don't have space to substitute back in here, but you can at least write down what you would do. So you remember w equals v over u, and v over u is y minus k over x minus h, and we know what those were. H was +2, and k was -3. So that's what we would plug in for w, and then u we know is x minus 2. Okay, so use that to substitute back in for that one. But once we get here, we're pretty much done. Just have to write things in terms of x and y. All right. Questions? Okay, good. That means that you'll be able to do this example, right? All right. I'll give you a while for this one since it's pretty early, and it takes a little bit to get through them. So go ahead, give it a shot. Yes, who has the attendance sheet? Oh yeah. If anyone else needs it, yeah. Oh, that's the idea. It's close to it's better to see it.
Are we going to like a huge like usage?
So I call that I do party. Yeah.
Just once. Watch John.
Yeah.
I just want to make sure I'm on the right track. Okay. You said x minus 3. Oh. It's like, yeah, so the last time we just that's why I did three. So also so we always need to do the double x and y substitution.
Yeah, this is one word, single substitution to start the word.
So we'll always have to, like, there'll never be an instance.
Not for
Alright, so just for all of us. Alright.
in a case where you can't do one substitution, well, if two substitutions still work. Does that make sense? Sorry? Yeah, you were saying like these are only two double substitution, right? Yeah. But in a case where you do have like one substitution, like two substitutions still work. It just may not be necessary, right? Okay. I can tell you for these like equations, there's no equation where that's just one if like if that was like x minus 3. Yeah, okay, no max. Right, okay. Then appreciate it.
Yeah, you might experience 3D.
Yeah.
And then cancel all this out.
I'm doing double. I'm gonna play doing all the. Oh.
And then we did.
I lost my. I'm working on it. I separated the wrong things. Yeah. You know when we like 1/2 of the equation equals 0. Yeah. Why? Disregard the other half. Because you're trying to figure out what you're trying to figure out what H and K are. Yeah, right. But like even when you're because it's in the function or whatever it is in the so H and K are just constants. So you're trying to figure out.
So you just leave U and B at U and B.
Yeah, that's why you guys like separate like that.
Right. But then when you're doing it, you're writing the equation again, leave U and B and plug it in. Right? Does that make sense?
You have the first one is H, second one is it's constant. How did you solve it? All right, so after you do that, you just plug it back. Oh wait, well they go. So it's like 7 plus 9 feet. So dogs from box. So it's it. It's it.
How do you solve
Start laughing. Separated weights. Yeah, so together it works. DVD experts. So, I don't know.
How we doing? Need a little more time or a little bit more?
Let's go till 5 and then we'll finish off in the last 15 minutes.
Slide that says what to do after you solve for ancient.
This one or which one were you asking about?
Like when you, yeah, that's.
This one? Mm-hmm.
I think she got that too. Although they don't allow it. Dude, that's yeah, I hate that. That's why I was so the last one.
Oh, right here. Right here. It's because so this just I love Oh, we do. Because it's one review.
All right, let's go ahead and finish this off. No? Okay. Good. But not 40 or not 20? $10 confident maybe?
Yeah.
5 to 10. You know, there are a lot of mathematicians back in the early 1900s who used to put money in like wine and sometimes peace on problems. Yeah. Yeah, but those are hard. All right, let's go ahead and get this one out of the way. So do we have space for a little bit here? All right, so we want to go ahead and solve this differential equation using what we already know. Now that we've done things the hard way, I'll give you some shortcuts. You have to struggle with things the hard way before you learn the easy way, right? Because then you don't have appreciation for the easy way. Also, you won't be able to do the easy way if you make a mistake. That's the big issue, is that if you do things the easy way first, you just get a formula, then when you make a mistake, inevitably, you won't be able to fix it and you won't know where that mistake was. If I could, I would just give you the formula right away. However, my students tend to get bad grades on tests if they do that. Okay, so here's our quick substitution. H and K don't actually matter until the end of the problem. Notice that way back here, do H and K show up here at all? No, not even a little bit. So what we can do to make our lives a whole lot simpler is just rewrite things immediately. So it's not going to be exactly equal, but dv du, oh, yes, it will actually, is the same as u minus 3v over 3u minus v. So you don't even have to go through all of that trouble of substituting things at the end. And then at the end, we'll do that, find h and k, and it will be a lot easier. So you just write that differential equation down immediately. dv du equals u minus 3v over 3u minus v. And now transform it into a separable one using that substitution w equals v over u, v equals u times w. And we know this one, so I'll just write down what it turns into here. W plus u dw du equals 1 minus 3w over 3 minus w. Okay, and for a little bit over time, I want to get through this quickly. W, we'll find a common denominator. And in the numerator, we should get w squared minus 6w plus 1. And in the denominator, we just have 3 minus w. Okay. So rearranging to make this look separable, I want to put du on the other side, up top, and then u on bottom. And I know that's a little messy. What it will turn into is 3 minus w over w squared minus 6w plus 1 dw, 1 second, equals du over u. Question? Here. This one? How did I get this part? So I'll do that one more time here. So that comes from this equation right there. So if v equals u times w, we think of w as a function of u, and then taking a derivative, you get dv du equals, okay, product rule right here, 1 times w as a function of u plus u times dw du. And so the one we just don't write, and we get w plus u dw du. Factor out the u here, or maybe multiply by 1 over u on top and bottom. Yep. All right, so now that we have this part, the right side is pretty easy to integrate. That'll give us log u plus c, right? And then the left side is a little trickier. It looks like it needs partial fractions. I'm going to claim that we don't actually have to do all of that. We can make this a simpler integral by doing some substitutions cleverly. What we can do is take this polynomial in the denominator, w squared minus 6w plus 1, and write it as a perfect square. And that now factors as w minus 3 squared minus 8. Okay. So that's completing the square. And then the very last part is that I want to get a, do I actually even need to do that? I don't think I do. Yeah, no, we can leave it like that.
We just have to add the 9 to both sides, though, right?
Well, there is no both sides. 9 minus 8 is equal to positive 1. So it's another way of completing the square. Okay, so that gives us minus w minus 3 over w minus 3 squared minus 8 dw equals du. Actually, let's write this way. So log u plus c, and we'll say that's the antiderivative now. And then the last thing that we want to do to get the answer here is take this whole bottom part and say this is a new variable z. dz ends up being 2 w minus 3 dw. Very close. We just have to add that in here. And now this part is dz. So let's take that to the other page. All right, so there's all of that. And I actually don't want to erase all of that. That'll give us a new integral here, 1/2 integral, or minus 1/2 dz over z equals log u plus c. And this is minus 1/2 log absolute value of z. Okay. So I think that we can go ahead and actually solve this one for y in terms of x. We only have a couple minutes left, so we might as well do that instead of getting some huge theorem that's going to take a bunch of time. Let's do that. So we have log absolute value of z equals minus 1/2 log u plus c. And then z equals, so we're going to do e to this thing, which should give us c times u to the minus 1/2. Then remember, we can drop the absolute value bars because we took this e to the c and wrote it as just c times u. And then z, well, z was a little tricky. That was w minus 3 squared plus or minus 8. Okay, and I do not actually want to multiply that back out. I want to leave it in a form where I can easily solve for w. Equals, where is it? C u to the minus 1/2 power. If you go ahead and solve this for w, you'll get 3 plus minus the square root of 8 plus c u to the minus 1/2. And then the last thing is to remember that w is v over u, and v over u is y. Now h and k come back in. Plus k, or minus k, sorry, minus k over x minus h equals 3 plus minus square root of 8 plus c x minus h to the minus 1/2. And then you can solve that for y pretty easily. We have 1 minute left. Let me go ahead and tell you how to get h and k very easily. So we have this for our differential equation, minus 4 plus 4 on the bottom, I think. Yes. When you put in x and y equal u plus h and v plus k, you will get exactly this equals 0 and exactly this equals 0 as your linear system of equations. So you don't have to plug in all that substitutions. Just write in u minus 3v minus 4 equals 0 and 3u minus v plus 4 equals 0. Solve that system and you get h and k immediately. Or not u, h. H minus 3v and then 3h minus v. Yeah, solve that and you get h and k. Can't figure that out today. Right away. Okay. So there's a couple more things that we'll do on Thursday. Remember, your homework is due then. And it seems like some of you think that we have a test this Thursday. We do not. No test this Thursday. Thank you.